Okay, let's move on to part B of the question. Part B is similar to part A, except there's a key difference. For part B, the table is allowed to move freely rather than being forced to move at a constant angular velocity. So if we think about what does that mean in terms of diagram, well, if this is the turntable, and it's spinning around like this with some angular velocity omega, omega is no longer a constant. Omega is allowed to change over time. In part B, we just need to find the velocity and the acceleration of the ball again. And to do this, we're going to borrow some of the equations that we actually used when we were solving part A. So we've got the force on the ball, it's given by this equation here. We've got the torque on the ball, it's given by this one here. And we're going to use the no-slip condition. Let's start with the torque equation. And then what we're going to do is we're actually going to integrate both sides of that with respect to time. So when we do that, we get something that looks like this. Okay, and noting that most of the things are constants, then what we actually get is this. Okay, and then what I'm going to do is just divide I through to the other side. And then I'm actually going to take the cross product of everything with respect to z and move omega naught to the other side. And for this term over here, the final term with the v minus v naught, we're going to use our triple cross product rule, and that's actually going to get rid of our z's, which is kind of handy. So let's do it. Okay, and now we're going to substitute this into our no-slip condition, because if you have a look, we actually have that this part here is the same as this here. So that means that we're going to get, and then we can do the same thing, except we can actually have it the no-slip condition when we have v is equal to v naught, or at time equals 0. So that's going to mean that capital omega is omega naught, capital R is capital R naught, and omega is omega naught. So that'll give us, okay, now I want to rearrange that for the omega naught cross ZR term, and that will give me, okay, and now if I have a look at this line here, I'm going to solve that for V, and I'm going to make a substitution for omega naught at the same time. Apologies, I missed omega naught should be crossed with Z. Alright, so I'm going to bring all my V terms to the left side. On my left hand side, and then on my right hand side, I'm going to get, okay, and then if we actually remember, we were given a nice definition for a shortcut term we can use called alpha. So in this case, we can see that our v's are actually multiplied by 1 over alpha. So, and if we gather our v naught terms, then we'll actually see that this is also equivalent to 1 over alpha. So that means that what I've got here is now, and then if we just multiply everything by alpha, then we have our expression for v. Okay, and then we can just differentiate that with respect to time, and we can get our acceleration. So this isn't actually too bad. So please note that when we differentiate, the omega naught, r naught, and v naughts are all going to go away. So that means that we are just left with a product rule to do for this term here. So take the derivative of the first term, and then take the derivative of the second term. Okay, and if we wanted to solve for acceleration and we didn't want it in terms of v, we could actually do a substitution here for the top line into the second line. Alright, and that's part B1 finished. Alright, so now that we've found the acceleration of the ball, we can actually use this to figure out how is this disk going to accelerate underneath the ball. And so the trick for this bit is we just want to look at what are the torques acting on this disk, and the torque on the disk is going to be essentially the negative of the torque on the ball. So if we write an expression for the torque on the disk, we're going to have, so the moment of inertia times the angular acceleration, which is in the z direction, just going to be equal to minus r cross f, where in this case f is m times the acceleration of the ball. The reason we've got this minus sign is that it's going to be like the disk is going to receive the opposite torque that the ball receives, so it's like an equal and opposite torque in this case. Okay, now the issue is here that they don't want us to use v or v dot in our final answer, so we're going to have to do some substitutions to get rid of this. So in the previous part, we had expressions for v dot and v. I'll just quickly write those down for us. Okay, and first thing I'm going to do is we're going to substitute in for v dot, or for the acceleration, which gives us, okay, and now we're going to use our triple product rule, and when we're using the triple product rule, what we're going to do is we're going to use these two identities here. So we're going to have r dot r just essentially equals a scalar r squared, and r dot z is going to equal 0, because z is pointing up and r is strictly horizontal. So then if we apply this triple product rule, we're going to get, Okay, and now we need to get rid of v, so we can substitute in our expression that we have for v, and we get... So just a quick note, because everything's in terms of z hat here, I can just get rid of that, which is nice. Okay, so now I've got that, let's keep going. So now everything's scalar. I'm just going to bring this first term to the other side, and just keep in mind all of this bit here is just r.v. We're going to use that trick a little bit later. Now if we want to, we can do a little bit of a simplification here using our triple product rule. Because we've got r dot and then you've got z cross r here, well, z cross r is strictly orthogonal to r, and then r dot something orthogonal to r is going to be 0. So that means that we can actually just get rid of this term in here. Alright, now we'll just write this out with a little bit of factorization. Okay, now they actually told us that there's this symbol delta that they'd like us to use, where delta is given by id over mr squared. So to be able to use that, what we're going to have to do is divide everything by mr squared. So let's do that. So this bit here is just going to become our delta. And sorry, I actually dropped these m alphas here. Apologies, I'll go back and fill those in, which means that these minuses are in the wrong places. Now let's cancel out the m's. Okay, and then we just have to divide both sides by this expression here, which will give us... I know that I've missed r dot here, so if you like, this has just got an r dot on the end. And what I'd just like to point out, because this is going to be important for our next part, that if I just highlight this bit in green, this bit here, this was actually all equivalent to v dot r. So we might use that when we're solving B3. Alrighty, so that's our B2 done. Let's move on to B3. Alrighty, for B3 we're going to need our result from B2, so I've just saved it on the right hand corner over here. Now essentially all we need to do is integrate this function with respect to time. However, there is one extra constraint they've put in the problem. They're not allowing us to have things in terms of v0. So first of all, we're going to have to find a way to eliminate our v0. Now in order to do that, we can do a little trick. So you might remember that everything that I've got here we decided that's underlined in green was equivalent to v dot r. Now, if we think about v dot r and we want to eliminate v so there's no v in it, there is this kind of trick that we can do. So let's imagine for a minute that we're going to take the derivative d dt of r dot r. So if we use the product rule here, then we're just going to get that this is v dot r. Now this is handy because the r dot r is essentially just a scalar. This is something that we can, and also it's a variable that we're allowed to have in our answer, which is really nice. So what we can then do is, if we just like divide both sides by 2, then we can get rid of this bit that's highlighted in green by essentially using that v dot r is going to be equal to a half dr squared dt. So we can substitute this in, and then we get this. Alright, I'm just going to do the denominator first, like this. Now, integrating the right hand side here is going to be a little bit difficult. Now, it just so happens though that if you look carefully, there's a little trick that we can do here. If we were to take this omega here and bring it to the other side, then we can actually write this like this, where we have the derivative of the function on top of the function itself. So that's really handy. Now I'm also just going to be a little bit careful in the way that I arrange this here, because if I just bring this minus 1 over 2 out the front, then let's have a look at this denominator. And now if I compare that very carefully with the numerator, it's actually going to look like this. And if you have a look, what we've actually got here is that this numerator is actually the time derivative of this denominator, because the only factor that depends on time is capital R. So what that means is when I integrate this, I'm going to have this nice relationship where the derivative of the bottom is on the top, which means that I can just simplify that to a log. So let's take the integral, time equals 0 to time equals t. Just to make this easier, I'm going to multiply the top and bottom by r squared. So if I do that, this goes away, and I get an r squared here. Alright, and now let's substitute this in. So on this side here, we're just going to get the log of this, and then we have to subtract off when it's equal to 0, like at time equals 0, so subtract off omega naught. And then here I've got minus 1/2. Okay, and now I'm going to use my log laws to get, and cancel the logs on both sides as well. So that minus 1/2 is just going to become a square root, and I'm going to flip these, so I'm going to have... Okay, and then I can just multiply my omega naught to the other side, and I therefore get... Okay, that's looking pretty good. I'd say that's our answer for B3 done. Now for B4, what they just want us to do is find the maximum possible value for omega. Now there's essentially only one variable here, and that's r squared that we can see here. So if we just set r squared equal to 0, that's going to give us the maximum possible value for omega. So if we just put that in its own little box here, and this value is going to occur at r equals 0, and the larger the r naught value was to start with, the larger this is going to be. And that kind of makes sense, because if the ball came from a really long way out and then kind of rolled in, then you can pick up more angular momentum as that ball moves in from further. Alright, and that's B3 and B4 done. Before we have a look at B5, it's going to be important that we just revise something called conics. So we'll just quickly go through that now. Alrighty guys, so before we move on to part B5, I thought that I would just talk to you about something that's going to be important for us to understand to be able to do this, and that is conics. Now conics is called conics because it's about looking at the cross sections of cones when you cut them at different angles. I'm not too worried about thinking about it in terms of cones. What's most important is that for you guys, I just want you to know that if you have an equation that takes the form of what you can see here, so I've just called up a website called Desmos, which is great for visualizing different functions. So if you have a look here, we've got ax squared plus bxy plus cy squared plus dx plus ey plus f. So this is the general equation for conics. And I've set f is equal to minus 10 for us, so we can just imagine we've got everything else on this left side equal to 10. And it so happens, depending on what parameters you put in for a, b, c, d, and e, you can get different shapes. And if you have, I've set everything to 0 except for a and c at the moment, and f of course, then you get a circle. Now if you play with d and e in this scenario, all that happens is you translate your circle. You do also increase the size of it, but the way that I just like to think of it in this case is that these parameters are primarily responsible for translations, and E is for vertical. A, B, and C are actually what are required for changing the shape. Now if we have a look here, so we start with an ellipse. I'm just going to get C to scroll through some values. So here if we have C change, then first it becomes an ellipse. So if we have a look, we're back at our elliptical stage, so circle to ellipse, and then it will spread out to become a parabola before becoming a hyperbola. And so for different values of C, in this case, you're going to get different types of functions. And it's similar with A, it's just changing in the x direction rather than the y direction. Now an important other term to think about here is you could think about, well, what's going to happen if we change B? And the answer is, maybe just to make it clear, I'll make it so we start not already on a hyperbola. So B essentially rotates your shape around. Okay, so those are our different parameters in a conic equation, and then what I want to show you now is a rule. I've copied this straight off Wikipedia, but this is essentially telling us the rules for when you get different types of shapes. So I'm not too worried about the matrix part at the top there. Don't worry too much about the determinant, but instead have a look at these rules that are in this bit here. So it so happens that if you have b squared minus 4ac is smaller than 0, then you're going to get an ellipse. Now you have a very special case. If a equals c and b equals 0, then you get a circle. Then we'll get a parabola when we have b squared minus 4ac equals 0. And if b squared is greater than 4ac, then you get a hyperbola. Okay, so this is the basics of conics I just wanted you to know before we go and explore part B5. Let's do that now. Okay, so part B5 is quite a long question with quite a few subparts. I've got it up on the screen here. What I want to do is just break this down and do it part by part. So the first bit they want us to do is they want us to find the angular momentum for the system, and they want us to find the part of the angular momentum that can change over time, so ignore any kind of constant components. So let's start by doing that. Let's write an expression for the angular momentum. So in this case, we're only considering the z direction of angular momentum, and we're going to call the total angular momentum mz. This is in the z direction. Now this has got contributions from two places. One, a contribution from the table, rotating, so that's just going to be given by the moment of inertia of the table, multiplied by the angular velocity of the table, and that's in the z direction. And then you've got the ball. Now for the ball, there's two components. There's the fact that the ball actually moves around on the table itself, and that could be contributing to the total angular momentum. Then you also have the fact that the ball could be rotating around like this. Now, this isn't exactly what we expect. We expect it to be kind of more rolling, but if it is rotating around, then it will have a component around like that, so we've got to add that on too. So first, let's use the position of the ball. So that's just going to be R cross P. So in this case, P is just going to be mv. And then we also have to add the component due to the ball potentially spinning about on its axis. Now, this final kind of component that we've got here, there's no way that you can actually change that rotation speed, at least in the frictionless case, because there's no way to apply torque to the ball. If you have the ball like spinning around like this, then the only way to apply torque to that is to have an off-center torque to that, but the only contact point is at the bottom of the table, directly below the center of mass, so there's actually no way to adjust that component of the angular momentum. So that means that when they're looking for the part that I guess can change, that isn't going to be conserved over time, then we're looking at our, we can get rid of that final term. So our L dot Z, when I say dot Z, I just mean L in the Z direction, is given by that. Now, just one thing I'd like to point out here, we don't actually need this for later on in the question, but it's just good to have in mind that later in the problem we're going to use L as a constant, and you might think, oh, why is it that we can just have L as a constant? Well, because it's conserved, it's also initial to the original conditions. So we could also just write that this L in this case is equal to this constant here, okay? So that means that now we kind of have permission to use L as a variable going forward. Now, the next part that they want us to do is they want us to refer to our answer in B1, and then they want us to write velocity in terms of C, where C is the part of the velocity term that does not depend on the position of the ball. So let's just rewrite what we had in B1. So we had V equals, okay, this term here, and clearly the only part that depends on the R is this first part here, so the rest of that is going to be C. So I guess therefore we have our C is like that, and that means that I could write V a lot more compactly now, like this, and we can actually substitute this into our expression for L. Alright, and now what I'm going to do is factor out all of the terms that have got capital omega in them. Okay, now what I'd like to do is actually solve for omega. That's the whole point of this question, and what I'd like to do is kind of make it so I'm not dealing with a vector anymore, I'm just dealing with scalars. So I'm going to take the dot product of all these terms with respect to Z, and then I'm going to use the triple product rule for my R cross Z cross R, which is going to give me a factor of R squared in the Z direction. Alright, so if we do all that, we're going to get, and just to clarify, R squared is like R dot R in this case. Alright, now the next thing they tell us to do is to line up the x-axis with C. So what this means is we can actually get some information about how R cross C is going to work. So in particular, what we can say is that we know that we could write R in general as x hat plus y hat. Now, if C is directly in line with the x direction, then when we take the cross product with R, then the x component is going to go away because they're not orthogonal, they're directly in line. So that means we're just going to get that y component, and then what we're going to have is we're going to have the y component of R crossed with x component of C. And when you take y cross x, or y direction cross x direction, you get minus z. So that's going to give us a minus sign here. So let's substitute that in. Sorry, I forgot to write that I was taking the dot product with z before. So, alright, so I have the y component of R left over, then I'm just going to call C without the vector symbol, the magnitude of C, and that's all going to be in the Z direction. Alright, and they prefer it if I use the symbol delta rather than ID in this case, so what I can do is I can just divide everything by M and also factor in an R squared, so that'll look like L over M plus YC delta. I need this R squared term. Okay. Alright, so now what they want us to do is combine this with our answer from B3 to eliminate omega, and that way we can find the trajectory of the ball. So, first thing we're going to need is our equation from B3, so let's write that in. I'm just going to multiply everything by R squared to make this simpler. Okay, and I can set that this omega squared in here is going to be equal to this expression for omega, which means that I'm going to get... Okay, and then the two denominators here are actually equal to one another, except this one on the left-hand side is squared. So I'm going to multiply the square of that up to the other side, and then I'm going to square this left-hand side over here as well. Okay, now at this stage, we just want to simplify some stuff out so we don't have to write out so much each time. So what we're going to do is we're going to call this entire chunk here, I'm just going to call K. Now this L over M, I'm just going to call lambda. And then I also just want to note that since we've got R is X hat plus Y hat, then R squared is just the dot product of R with itself, so that's just X squared plus Y squared. Great, and then we can just substitute all of that in and expand it out, and we're going to get... Alright, and what I want to do now is just rearrange this so it kind of matches my conics formula, so it looks like A X squared BXY plus C Y squared plus D X plus E Y equals minus F, where we actually want minus F to be positive. Alright, so let's do this. So for my X squared terms, I've got alpha K X squared. For B, the XY, I've got nothing. Okay, for Y squared, I've got K alpha minus C squared, Y squared. DX, I've got nothing. For just the Y, I've got 2 lambda CY, and that leaves me with lambda squared minus K R squared delta as my F term. If you recall everything that we were saying about conics before, essentially if we have a look, the parameters that are going to determine what our shape is here is, okay, B, but that's 0, so that's not interesting. Then we've got A. Now I'd just like to point out at this point, if you're looking on for the official solutions, I actually have something slightly different. They have an extra factor of alpha with their A, like they have an extra factor of alpha just here, and they've got an extra factor of alpha with the K and Y squared. Now I cannot see how they got that, so I believe what I've written is correct, but if somebody thinks that I'm wrong, please let me know and I'm happy to go back and change this. So I have A equals K alpha, and I have C equals K alpha minus C squared. Now the key factor that we needed for this to work is we always looked at 4AC and how it relates to B squared. So in this particular case, if we have AC is greater than or equal to 0, well actually if you have a look at A, K is strictly positive and alpha is strictly positive. So only C can be negative. So really C is the determining factor here for whether or not for the different shapes we get. So if we have AC is greater than 0, then we'll get an ellipse. But this is strictly K alpha greater than C squared. Alright, if we have AC equal to 0, then we get a parabola. And this is going to be K alpha equals C squared. And then if we have AC smaller than 0, we get a hyperbola, which means that K alpha is smaller than C squared. Alright, and that's part B done. Now we just got to do part C.